So it is a very good pleasure for us to introduce today's speaker. Professor Nikolaos Dimakis, who is actually talking about the time operator from parametrization, invariance, and implication for cosmology. And I think that's where you can start off.
Okay. Let me share screen. Okay. Can you see it?
Yes.
Yeah. Okay. Nice. Well, thank you very much. I want to thank you for organizing this talk and for giving me the opportunity to present this work. As you see, I'm going to talk about a definition of a time operator in a certain class of parametrization invariant systems. And in particular, we're going to see parametrization invariant systems that are used to describe the motion of massive particles in a generally curved space. And the reason why I'm interested in this type of system is because they can actually be used to model cosmological configurations. And we will see this analogy also. Well, the plan of the talk is the following. First, I'm going to introduce the general geodesic system, what kind of Lagrangian we're going to utilize. Then I will define what I call non-local conserved charges. Actually, it is one of these charges that we're going to use at the quantum level to define the quantum time operator. In section 3, we are going to see the analogy to cosmological Lagrangians between the geodesic Lagrangian and cosmological Lagrangian. I will introduce the time operator in the next section, and before finishing, I will demonstrate a few examples, one in the geodesic problem, considering a free relativistic particle moving in flat space, and the other giving a cosmological example. So let us first start with a general geodesic problem. And in order to begin here, we have first to pick a Lagrangian, because there are quite a few different options that one can use to start the geodesic equations. For example, we have this first Lagrangian that we see over here, which is what I call here the affinely parametrized Lagrangian, because if you vary this in order to obtain the Euler-Lagrange equation, you will get this set over here, which is what people usually refer in the literature as the geodesic equations. However, it is not the most general description of geodesic equations. These are the geodesics that are related with n-affine parametrization along the curve, or in the case of massive particles, what we call the proper time of the particle. Now, this Lagrangian, it is, as you see, quadratic in the velocities. As long as the parameter is conserved, as I mentioned, it is the affine parameter. So the only thing we can do here are constant translations, which are symmetries of this action, of the corresponding action. And as we know, this implies the conservation of the Hamiltonian, of the energy of the system. The second Lagrangian, it is the well-known square root Lagrangian, where you basically here ask to extremize the length along the curve. And this is actually an example of a parametrization invariant Lagrangian. The corresponding action remains invariant under arbitrary changes of the parameter. The Euler-Lagrange equations you can see over here. You can notice that on the right-hand side, it has something extra. This is due to the parametrization invariance. If you choose the affine parameter, which corresponds in taking this inner product of velocities to be a constant, then you obtain the previous set of equations. The difference here of this Lagrangian, a bad property that it has, is that it doesn't have any Hamiltonian. If you try to calculate a Hamiltonian, you will get identically equal to 0. So you can do no phase space analysis using this Lagrangian. This is a problem which is remedied in the third Lagrangian over here, which you can find in the literature as the geodesic Lagrangian in the Einbein formalism. The Einbein is this field that you see here, this E, which serves as an auxiliary degree of freedom that helps us reproduce the Hamiltonian constraint, as we're going to see. Now, this is a quadratic Lagrangian, but this time this is a parametrization invariant. You can still make arbitrary changes of the parameter as long as the Einbein transforms in this manner. Basically, you want the Einbein field to transform as a velocity. The difference with the previous case is that now the Hamiltonian is 0 on mass L when you substitute the solution of the system, but it is not identically 0. It exists as a function in phase space, and thus you can use it in order to generate dynamics. The Euler-Lagrange equations here, you can see them over by this set. You have the second order equations that correspond to a variation with respect to the position, and additionally you have an extra equation of motion that is the Euler-Lagrange equation for the Einbein field. You can notice that if you solve algebraically this last equation with respect to the Einbein and substitute in here, you will obtain this set of equations, the ones corresponding to the square root Lagrangian. Now, this Einbein Lagrangian has an extra good property because it can also be used in order to study the motion of massless particles, or photons, let's say. This is a problem that this Lagrangian cannot describe this type of geodesics, because if you notice at the corresponding Euler-Lagrange equation, this inner product for photons, for massless particle, has to be 0, and it appears in denominators if you carry out this calculation of the derivative. So its equations, they're not well defined for photons. For this Lagrangian, this is no problem. Here, you just need to put the mass equal to 0. This term will get eliminated. You get the null condition for the velocities from the Einbein equation. The Einbein field remains arbitrary, and you have this equation well defined. If you want the affine parametrization in this case, you will set the E to be a constant and return into this case of equations. So this is the Lagrangian that we're going to utilize because it has all these good properties. A Hamiltonian that is 0 but not identically 0. And also it can describe without problem the trajectories of photons. And if we start now to look at the symmetries of this Lagrangian, and now not at the infinite dimensional symmetry group that has to do with the parametrization invariance, but symmetries that will give us conserved charges. And in particular, if you try to look for what we call point symmetries, basically in this case, they are symmetries generated by vectors of the space where the motion takes place. We will see something interesting. Trying to calculate through the symmetry criterion invariance through the Noether theorem, the symmetries of the problem, we will see that if we choose the mass to be 0, then we will obtain all conformal Killing vectors fields of the metric which satisfy this relation over here as symmetries of the problem, generating linear in the momenta conserved quantities of this form. But if we take the mass not being 0, if we consider massive particles, then we will obtain a different group, a subgroup of the conformal Killing vector, just the Killing vectors, which have this action of the Lie derivative leaving invariant the metric. And again, the corresponding symmetries, they will be of this form, linear in the momenta. But we experience here what we call an explicit symmetry breaking. We have a parameter inside the Lagrangian, the mass, and depending on the value of the mass, we either get a bigger group, the conformal Killing vectors, or a smaller group of symmetries in the system. And one may wonder here what happens to these missing symmetries. Because if one takes notice of the equation needed in order to obtain the symmetries of a given Lagrangian, you will see that they're, of course, partial differential equations, but they are linear. So one would expect that under certain, let's say, smoothness conditions, you would expect to have some symmetry generators that depends continuously on the parameter, that you do not see this discontinuity, this jump from this group to this group. And as we're going to see, there is such a continuity. The reason that we're missing it here is because of these assumptions, because we assumed that we looked for symmetries that are just vectors of the space-time. If we relax this condition, we will obtain what I will define later as the non-local conserved charges. But in order to derive them, let us first go to the phase space and write the Hamiltonian. It will be easier to see there what happens with these conserved charges. In order to write the Hamiltonian, because this is a constrained Lagrangian due to the parametrization invariance, one has to use the Dirac-Bergman algorithm. I will not go into details about this algorithm. The end result is that you get the Hamiltonian that you see in equation 1. That is a linear combination of two constraints. One constraint is that the momentum of the Einbein has to be 0. This is a trivial constraint because the initial Lagrangian does not have any velocity for the Einbein, so trivially its momentum needs to be 0. And one also gets this, which is referred as the quadratic or Hamiltonian constraint. This is the quantity that I mentioned previously, that it is 0 on Massel, but it exists as a function in phase space, so it can be used inside Poisson bracket in order to generate dynamics. And this Kerley equal that you see over here and here, this is basically in order to, it is called the weak equality in the Dirac description of constrained systems. And it's basically used as a rule to remind us to not set this quantity 0 when appear inside Poisson brackets. We can project the result of the Poisson brackets into the space, the subspace of the phase space where these equalities hold. And this is the formal definition of a weakly 0 quantity. If we say that this is weakly 0, it means that the quantity is 0, but its divergence in phase space, the derivatives with respect to positions and momenta are not 0. And this is why it is important to not set it 0 inside Poisson bracket, because Poisson brackets involved this calculation. Now, the existence of constraints in a system can help us expand what we consider as a conserved quantity. And Kuhar was the first who noticed this. He defined what he called conditional symmetries, which it's basically the following. In a regular system where there are no constraints, normally for a conserved quantity, we would consider that if a phase space function, let's say we want it to be conserved, that its derivative with respect to the parameter or to time in general, it has to be 0, which is equivalent to the Poisson bracket with this quantity and the Hamiltonian being 0. However, if constraints are present, Kuhar noticed that I don't really need to set this strongly equal to 0. I can set it weakly equal to 0, which is equivalent to saying that the Poisson bracket needs just to be something proportional to the constraints. In our case here, the Hamiltonian. The Hamiltonian is going to be 0, and thus the quantity will be conserved. And you can notice that equation 4 here is a generalization of 3 because it is basically the inhomogeneous version of equation 3. If you see it as partial differential equation for the derivation of the phase space function, which is conserved. So this one, equation 4, contains the solution of 3 and possibly something extra. However, for this particular Hamiltonian, for the geodesic system that we have here, if you consider this type of function and try this condition, you will not get anything new comparing to this situation over here. The new quantity will emerge if you allow also the phase space function to also depend explicitly on the parameter. If you do so, then you can see that you can define the following non-local conserved charges, which are of the form that you can see in equation 5. Here you have a linear part. This is the local part. The Xi is a conformal killing vector of the space with a conformal factor omega, which this conformal factor appears inside this integral. And it is because due to this integral that this is a non-local conserved charge, in the sense that it involves an integral of functions of a function in phase space. And notice that this non-local part is multiplied by the mass. Now, if you take the total derivative of all this quantity, you will see that this is the correct addition in order to produce something which is a multiple of the Hamiltonian, which is 0, and thus this quantity is conserved. So now we see what happened to those conformal killing vectors that we lost as symmetries when we turn on the mass. They actually mitigate to a totally different type of symmetries, a non-local symmetry generating this type of charge. And from this, we can see that we can connect with the previous result. If Xi, for example, is a killing vector, which means the conformal factor is 0, then the non-local part is eliminated, and we obtain the expected linear in the momentum conserved quantities for all killing vectors. If the particle is a photon, if we have a massless particle, then again the non-local part is eliminated, and again we obtain the expected linear in the momental quantities, now for all conformal killing vectors. But in general, if we have a massive particle, the proper conformal killing vectors still generate conserved quantities, but they are of this more complicated form. Now, I want to make note of something interesting here that we're going to use also later. If you consider that the space-time has a homothetic vector, this means that the omega, the conformal factor, is constant. We can normalize it to 1, as I did here. And you also consider the affine parameter along the curve, which corresponds to having a constant Einbein. Again, I normalize it here to 1. Then this conserved quantity assumes this local form now with an explicit dependence on the affine parameter, or if you prefer, on the proper time of the particle, and it is related linearly to this expression. Notice here that this conserved quantity is actually a conserved quantity that comes out of a symmetry of this affinely parametrized Lagrangian. The homothecy here exactly generates this type of conserved quantity, where the Hamiltonian appears here in terms of this m square c square. So now, here I just wanted to complete this analysis, just demonstrate the Nether symmetry generator of the no-local conserved charge. It is the one that you see in equation 9. And if we use this to see what type of change it affects on the Lagrangian, you will get this condition. And you see if this Xi is a conformal killing vector, then this is 0. And this generator leaves invariant the Lagrangian. So what I described as a Nether charge, as a non-local conserved charge previously, it is a Nether charge, a result of a Nether symmetry. Now let us see what is the analogy of this type of Lagrangian to cosmological Lagrangians, because up to now we just talked about a geodesic system and motion of a particle moving in a curved space. In cosmology, we start from a gravitational theory. We have some action here. I take as an example the Einstein-Hilbert action, possibly with some matter contribution. And of course, we know that if we variate with respect to the metric, we get Einstein's equations. Timunu here describes the energy momentum tensor. And in cosmology, we assume spacetimes that have certain types of symmetries. For example, we consider that the spacetime is homogeneous, which in this case means that we can split the variables. We can find coordinates with the metric looks like what you see in equation 13. You see that the t dependence here is separated from the x dependence for the dependence in the spatial variables. And in the case of homogeneous spacetimes, these functions are known, and one has to solve Einstein's equations for these functions of time. The Einstein's equations, in this case, they reduce to ordinary differential equations for these unknown functions. Now, one can, instead of substitute this metric inside Einstein's equations and obtain these ordinary differential equations, you can also do a different substitution one step prior to this. You can substitute this inside the action. And if you do so, then you will see that the action also splits in a part having the x dependence, which, however, involves known functions. And if you integrate in a finite volume of space, this will give just a constant. And it also will have a dynamical part that will only depend on time. And here you can have some Lagrangian, which will have the form that you can see in equation 15. Here you have the lapse. This is what we call the mini superspace metric. The Q's in this case, they correspond to the gamma alpha betas that you have here, and possibly any matter field that you can add. These Q's are basically the scale factors in this matrix here, in this metric. However, I need to notice here that this procedure of substituting the base manifold metric inside the axiom not always works correctly. You always need to check that this Lagrangian, as Euler-Lagrange equation, reproduces correctly the result of Einstein equations after you substitute this in here. These two processes do not always commute, so you always need to make this check. But let us consider that the Lagrangian we obtained from such a substitution, it is a valid Lagrangian and reproduces correctly the result that we want to obtain. The V0 that you see over here is the constant that I mentioned earlier that comes out of the integration of the spatial part. It's just an overall constant multiplying this Lagrangian. You can notice that this Lagrangian, it is quite similar with the geodesic Lagrangian we had previously. The difference is here that we have a non-trivial potential part, this VQ, but we will see that there is a connection. We can actually write it as an exact geodesic Lagrangian, this one. The Hamiltonian description is quite similar as before. Only difference now is that we have the lapse instead of the Einstein field here. We have also the two constraints, the momentum with respect to the lapse zero, and of course the Hamiltonian constraint also with a non-trivial potential. But exactly due to the fact that these are parametrization invariant Lagrangian, this parametrization invariance, we can also realize it in terms of reparametrizing the lapse function. You can see that the lapse is basically connected with transformations in the time variable. So such a reparametrization has a correspondence to a time reparametrization. For example, we can choose here the lapse to be given in terms of a new, let's say, lapse, but I will use a different lowercase n letter for this. And the connection between the two is this one. Then the Lagrangian we had previously, we will assume this form that you see in equation 19. And you will see now that this is exactly the same form as a geodesic Lagrangian, where instead of the metric of the space where, let's say, the particle is moving, we have this metric over here. It is the old mini superspace metric multiplied by what we had the potential in the original cosmological Lagrangian. But basically, this means that under a parametrization, we can formulate a cosmological problem as a geodesic problem, as a problem of some particle moving in a curved space. And one can use, of course, the exact same conserved charges as we had before that can be defined for any conformal Killing vector of this now metric, of this combined with a potential mini superspace metric. So we have a direct analogy with a geodesic case. And of course, here also we have these charts that I demonstrated previously for a homothetic vector and for the proper time when this lapse will be equal to 1, we will have a conserved charge which involves a linear in the momenta part and a linear in the proper time part. And it is exactly this which I will use as a guide in order to define a quantum time operator. If we solve with respect to the time parameter here, up to an additive constant, we have this relation that you see over here, and it is this function in phase space that I will try to write as and realize as a time operator. So let us go to the quantization of the system. And let us first start with the Hamiltonian. And for the Hamiltonian,
Hello,
sorry?
Can I ask a question? I had a question.
Yes.
Can you go back to your previous slide?
In the previous, this?
Yes. from equation 23, does it indicate you have used some gauge fixing condition where you identify the proper time with some phase space function?
Yes, it is in the case of the geodesic Lagrangian, it is exactly what we would call the proper time. It is when choosing the Einstein field to be a constant, which would correspond to the proper time of the system, or let's say the affine parameter along the curve. For the cosmology case, this is more complicated because it is not the original cosmic time, let's say, because we made a reparametrization in the lapse. So it depends there. In that case, it is a different time, not the cosmic time.
I understand, but the point is that without this equation 23, your entire analysis is based on the first class constant analysis, right?
Yes.
The first class constants. Now, with this equation 23, whether you have some second class constant or you have still the first class constant system.
No, here formally I should add some Lagrange multiplier in the Hamiltonian and fix it. It would turn the first class constraint into second class constraint. Here I'm just looking what is the relation of the proper time with a phase space quantity after performing a gauge fixing. It would give the same result, but I'm not doing the whole procedure from starting and fixing in the at the Hamiltonian level.
Okay, okay, fine.
So now, in order to go over to the quantization, we have this Hamiltonian. In general, you have the factor ordering problem. In order to address this here, I choose the conformal Laplacian. One could also use the normal Laplacian. I prefer the conformal Laplacian because it also has certain invariance under conformal transformations of the metric. And what we did at the cosmological level, this change between the old and the new lapse is basically a conformal transformation between this of this metric into this metric. So in order for this, I'm preferring to use the conformal Laplacian. In any case, the two operators, the conformal Laplacian and the normal Laplacian, they are identical in 2 dimensions, as you can see here, or when the Ricci curvature of this metric is 0. The mu is what we call the natural measure. It is the determinant, the square root of the determinant of this metric. The minus is used because these metrics generally have a Lagrangian signature. So according to Dirac's prescription for quantization of systems with constraint, we have to use at the first class constraints. When acting on the wave function, they need to produce a 0. This is clear for this constraint. The momentum corresponding to this lapse acting on the wave function has to give a 0. It basically tells us that the psi here will not have a dependence on n. The other condition defines in cosmology what we call the Wheeler-de Witt equation. And one can see that the Hamiltonian operator that we define using this conformal Laplacian for the kinetic part is also a Hermitian operator. Now, I want to construct an operator corresponding to this phase space function. And the most general linear expression of first order in the derivatives is what you see in equation 26, and which is also Hermitian under the same measure mu. So this is the most general operator that I need to use. I can use here for such a type of an expression. And the Xi, in order to connect it with this, I want it to be a homothécy of this metric. So this term over here, this divergence is going to be some constant. Now we can make use of some symmetries that the conformal Laplacian has. And one can find that if you define this operator, that you can see that they look like this one, their difference is just some constant factor over this part, then these two operators satisfy this type of symmetry relation with the conformal Laplacian. And from this equation, we can now see and derive that the continuous action of the operator that I defined previously and the Hamiltonian gives something which is constant times the wave function of the problem. But according to direct descriptions, we need these wave functions to satisfy the Wheeler-DeWitt equation. So trivially, one can add a Q over H over psi and write instead of this, where this now is the canonically commutation, the commutator of H with Q acting of psi giving such a constant. And in order to complete now this analysis, I will define the time operator in the following manner. I remind here that the classical expression of the gauge fixed version was this. Here in the definition, I will use 1m less than appears here. This is for dimensional reasons. If we go back at the Hamiltonian, you will see that it has m squared c squared. If I divide with an m here, then this will obtain dimensions of energy. So I will use 1m to divide over the Hamiltonian constraint and the other mc squared to divide this Q expression. And the previous relation that we had will take this form. And now this looks like what one would expect from a time operator, the canonical commutation relation that it would satisfy with respect to the Hamiltonian. And also we can make use of the Wheeler-DeWitt equation and what I wrote previously to analyze the action of the Hamiltonian over the wave function in this manner, using as this E, this combination, the H bar squared multiplying the conformal Laplacian, and this works, as you see, as an energy operator producing the rest energy of the particle multiplying the Hamiltonian. And with this operator, what I wrote previously, satisfy this relation over T. So you have an energy corresponding to the rest energy of the particle, commutate the relation with what I defined as a time operator, satisfying this, which one would normally consider that it implies time energy uncertainty relation of this form. You will, of course, remember from quantum mechanics, we have a position and momentum uncertainty relation that stems exactly out of a canonical commutation relation like this. But in the case of time and energy, one supposes the existence of an uncertainty relation, but there is no analog, there is no canonical commutation relation, because in regular quantum mechanics, you generally don't have some general prescription for a time operator. We see here that in this case, we have such a relation, but I'm not sure about this relation. This is why I put a question mark here, because there is a subtlety in constraint systems that differentiates them from the regular case. In the regular case, you would have the Hamiltonian, which can be any constant. But in the constraint system, this energy, let's say, or if you prefer at the classical level, this part, this cannot be any constant. This is supposed to be a fixed number in a constraint system. So it's normally it's not allowed to vary. This is what differentiates a constraint from a conserved quantity. A conserved quantity can be any constant. A constraint has to be a fixed number. And this is why I put this with a question mark here. And maybe it does not make sense here to talk about a time energy uncertainty relation, because there is no such uncertainty, because this has to be a fixed number. But anyway, if one sees this as an eigenvalue equation, then maybe you can interpret this as an uncertainty relation. So let us proceed over now to see some examples. And first, I will start with a relativistic free particle, a particle moving in Minkowski space. The Hamiltonian constraint here will take this form. This is, I'm not starting from the original Lagrangian, I'm just writing how the Hamiltonian constraint looks like. And if you turn this into operators, then you obtain the well-known Klein-Gordon equation of this form. And in any textbook, you can find how you can make an approximation to obtain a Schrödinger relation out of the Klein-Gordon equation. You basically assume this ansatz for the wave function, and you consider that the rest energy, the MC squared, dominates all other energies. Any term that appears divided by C squared, you depreciate it. You consider it to be zero. So if you do such an approximation, such a substitution and an approximation in the Klein-Gordon equation, you obtain a Schrödinger equation for this psi. Now we will try and do the exact same substitution and approximation in the result of the time operator that we defined previously. And first, we have to construct it. The homothécy of the Minkowski metric is this vector, and if we use the same formula that I used before to define the operator, this one, where Q is the operator that I defined here in equation 26, then we will see that under the same ansatz, the action of this operator on the wave function reduces to just a multiplication with the time variable over the wave function. So the same approximation that turns the Klein-Gordon to a Schrödinger equation makes this differential operator in just a simple time variable, the simple time variable multiplying the wave function. This I find quite interesting in this case. Now, in cosmology, things are less clear. And as a cosmological example, here I will consider the Lagrangian that comes out of taking an FLRW spacetime with some spatial curvature K, and in the presence, for the simplest case, of a massless scalar field, do not have some extra potential. If you make the mini superspace reduction that I described previously, the Lagrangian that you obtain will be this one. The V0, as I said before, is just the integration over a finite region in space, some fixed constant. And here you have the rest of the parts of the Lagrangian with the lapse function entering here. Performing the same reparametrization that I described previously, you can turn it in a geodesic, in quotation marks, Lagrangian, where the metric of the space where the motion takes place, you can read it from the kinetic part. And this metric, if you see from here, it is this one in this case. And it has a homothetic vector of this form. The Hamiltonian constraint of the reparametrized version is this one. And according to the previous description that I gave, the what I call the classical version of the time variable will be in terms of this function in phase space. So we will want to make this into an operator. And one can see that if you calculate the if you write down the Wheeler-de Wit equation using the Laplacian in this case, and writing the time operator in the same prescription that I described previously, they satisfy the relation that they are supposed to satisfy. Of course, for any function satisfying the Wheeler-de Wit equation. This is a necessary condition in order for this to hold. Now, I tried to make a connection to a Schrödinger equation here. It is a rather crude approximation. What I did is use the time, the classical expression for the proper time, let's say, in terms of this phase space function, and construct a canonical transformation, such a transformation is the one that you see in equation 51. If you substitute this inside the Hamiltonian, then the Hamiltonian constraint assumes this form. I also exploited here the fact that the Hamiltonian constraint is 0 to multiply with this exponential in order to decouple it from the kinetic part. And if you now consider some region where A is very close to 1, so that the momentum here will be very close to 0, and at the same time, the velocity will vary very slowly, which will allow you to consider this going to 0, then this approximates into this expression. And you can see that if you try now to make a quantum version of this, you have a linear expression in this time, in this momentum of time that I defined previously, and this would produce a Schrödinger equation. But I admit this is a very crude approximation, just trying to construct by force a Schrödinger equation. But it is interesting that there is actually, if one sees the classical solution of this system, there is actually a region which supports these two conditions that lead into this approximation. So now, in order to sum everything up that we saw that you can define non-local conserved charges corresponding to non-local symmetries in parametrization invariant systems that describe geodesic problem or cosmological problems for that matter. And you can use one such symmetry as a guide to define at the quantum level an operator that seems to satisfy a canonical commutation relation with the Hamiltonian, as long as the Hamiltonian satisfies the Dirac constraint, the wave function satisfies the Dirac constraint condition. And maybe in some sense, you can define some time energy uncertainty relations. I'm not still decided on this matter. And it is interesting to see what future applications one can have in cosmology in this case. Because in cosmology, things are less clear than they are in the description of the geodesic problem. Because you will have, in case by case, you will have different constants involved, different interpretations, different connection with the cosmic time. The situation is not so clear. So this is all I had to say. Thank you very much. And if you have any questions, please ask me.
I think it's a very nice talk. I think it's time for questions. Any questions? I have a few remarks on your work. Basically, you have just provided a description of energy, time, like uncertainties. And my question is, how to interpret this time operator and how it is related to the evolution of the state? Because to define the evolution of a state, we need some parameter in Schrödinger equation, and you know that the time is just a parameter to define the evolution of the state. But according to the Wheeler-DeWitt equation, this state actually annihilated by this Hamiltonian, so the state is not evolved with respect to some parameter. So how your time operator is related to the evolution time? Are there any correspondence between them?
Actually, this is my question also. This is something that I'm trying to understand as well. Because here I based all the construction into making satisfy a canonical commutation relation with the Hamiltonian. But in terms of the
I
motion of the
understand. I understand. So if you have some operator which satisfies the canonical commutation with Hamiltonian, why this is called time operator? Which qualifies it?
Yes, it's in the case of the one can argue that in the case of the geodesic problem, at least, where you can connect that Hamiltonian with the energy, you have a reason to consider it as a possible time operator. Now, for the cosmological case, basically there, in my opinion, one could define multiple time operators because I personally consider any internal, let's say, time choice that you can make in the system and compare all the other quantities, how they vary with respect to this internal time, it is a valid choice. This is an internal time in this respect, but with the extra good property that seems to satisfy this canonically commutation relation.
Okay, but there's another problem. If this operator T satisfies the canonical commutation with the Hamiltonian, according to the Pauli's objection, this Hamiltonian will be unbounded. It's no longer bounded from below. Then how we can say that this is a physical Hamiltonian?
This, actually, there are some papers over this because
I mean, how to avoid the Pauli's objection to time cannot be operated.
Yes, because Pauli said this, but not in a form of a theorem, because never provided a proof of this. And there are papers that there are some subtleties that have to do with a range of the dominion of the operator, the domain, the range of the domain of the operators. And one can avoid this restriction. But this one should check it in its system separately, I guess.
Yes, but you see, according to the position momentum commutator, which is also canonical, XP commutator is IH bar identity. And due to this canonical structure, you may notice that this position and momentum operator no longer be the bounded operator. And it's also not a trace class operator. So, but you know that in quantum mechanics, Hamiltonian should be bounded from below and should be trace class. Then how one can argue this Hamiltonian should satisfy that criteria, or it is not necessary in this case?
No, this is what I mentioned. There are papers where actually prove and have examples of bounded Hamiltonians that can admit such an operator.
Okay.
It's not a theorem that says that it cannot be done. There are counterexamples to this.
I see. Okay. And another question is that can you go back your previous slide where you have defined your time operator in a general concept?
Stop me if you see it here or before.
Yeah, no, I think it is in equation 32. In equation 32, can I interpret this commutator bracket with T and H at the level of classical situation just replaced by Dirac bracket?
I didn't try with Dirac, but with
Because this seems to indicate that Hamiltonian itself a constant and time operators must be satisfy some constant. So two constant if not commute, they satisfy the second class constant and it should use some Dirac bracket.
If you use Poisson bracket exactly with the Q, where is it? Here. If you use Poisson bracket exactly with this quantity, you will see that the Poisson bracket satisfy this expression. I used the gauge fixing basically.
But using this Poisson bracket, you will have so you are saying that the bracket between H and T in the Poisson level is just strongly zero. No.
No. The Poisson bracket, this with the Hamiltonian is not zero. It gives a constant.
No, I understand. Okay.
The definition of the homostatic vector.
Okay.
In order to give zero, you would need the non-local conserved charge. It is this whole combination. This is in the gauge fixed version, but if you do not fix the gauge, yes.
My concern is that you have used the gauge fixing condition, because when you introduce this what is your
It's
this in the expression
actually
of tau, this tau is related to
I
the
I cheated a bit because I used the gauge fixing condition to see to which phase space function the proper time would correspond. But then later, both at the classical or at the quantum level, I did not use a gauge fixing condition. I just saw what Poisson bracket this quantity would satisfy without fixing the gauge. And also at the quantum level. So I did so just at the level of the integral of motion to see what is equal to what I call proper time. But later in the analysis, I know where fix the gauge.
I see. Okay. Okay, I understand. Thank you.
Can I?
Yeah.
Nico, thank you a lot for your talk. Okay, I mean, you started from very well from classical particles going to the mini superspace description. However, do you believe that, do you think that it will be possible to generalize this in the case of the superspace? Meaning, let's say we have the idea of formalism, and we have a superspace that's reduced to mini superspace, and you apply this. So do you think that if you go before, we apply?
I'm not sure. There is the complication that there are extra constraints. For example, in the classical case, in the mini superspace, for example, you can have integrals of motion of this form satisfying, let's say, this condition. But for the full gravity, the extra constraints because of the shift vector there, they kill everything and they leave no symmetries, at least no symmetries of this form. Now, if one consider non-local symmetries at that level, I don't know what would happen. Maybe possibly can be extended.
Okay. Thank you.
Are there any other questions? Okay. Okay, so let us thanks Abdikar again.
Thank you very much for the invitation.
Very nice presentation.
Thank you.
Please share your slide. It will be useful for us.
So thank you very much. Goodbye, and I would very much like to be there with you, but the distance is very long. Thank you. Bye.
Next time you will come. Yeah.
Yes, next time. Okay. Thank you. Bye.
Bye.